Your textbook gives it to you, but just in case you didn't pay attention, right? There are little mnemonics that people memorize to help you remember what oxidation reduction means, right? Oxidation is a loss of electrons, reduction is a gain of electrons, right? There's also this one, loss of electrons is oxidation, gain of electrons is reduction. I just feel like that's more work to memorize. I just memorize that oxidation means gets more positive and reduction means gets more negative, right? Reducing, less, getting less. That's how it works in my head. Anyway, let's look at this. A redox reaction, right? We have our reactants, right? In order to know that it's a redox reaction, this, huge, right? We have to assign oxidation states. If I ask you, is this a redox reaction? And you say yes or no, the end, it's wrong, right? You have to tell me why, right? And the why is because I assigned oxidation states and I can tell that my manganese is oxidized and my hydrogen is reduced, right? And again, has to happen as a pair. Going back to types of reactions up here, right? We know that this is going to produce hydrogen, and we see that that hydrogen selectively comes from the actual place, right, where my two reactants are mixing, right? And slowly but surely this is happening, which is why actually if we took it out before it was done reacting and we looked closely at it with a really, really good magnifying glass, you would actually be able to see pitting, right, or the deformation of the flat surface, right, where it's reacting with the surface and taking off some of the atoms, right, but not all of them, right, and you'd be able to see that on the surface of the substance. And if we were going to depict this at the particulate level, right, we would have our H2 gas, where my hydrogens would be stuck together, floating around, right, above the fray for the most part. We would have our Mg solid hanging out in here, and we'd also have a plethora of ions, right, from the magnesium, from the chloride, right, all hanging out together. Okay. So are these redox reactions? I don't know. Let us see, right? Hydrochloric acid decomposes to form this, right? Chlorine's well, let's do this one. CO, this is obviously this. Okay. Now let's go ahead and assign some oxidation states. So HCl, this is -1, this is +1, this is, right, this is, therefore we could say that hydrogen is, what? Reduced, yes? Hydrogen is reduced because it became more negative, right? Chlorine, on the other hand, is oxidized. Chlorine is oxidized because it becomes more positive, right? Which is why it doesn't have to actually become positive, nor does it have to become negative. It becomes more positive or it becomes more negative, okay? Okay, so this oxidation state is 0 because it's an element. This is, hydrogen is generally +1, which makes this +4, which means that carbon must be -4, right? We go over here, this is -2, which makes +4. And this is -2 +1, yes? Well, as in like this is -2, so this is +2, there's +1. Okay, so if we take a look at this, we can see, right, that oxygen goes from 0 to -2, so we could say that oxygen is reduced, and we could say that carbon is oxidized, yes? Making this, overall, a redox reaction. And in general, when we have elemental things in either side, usually that's a big clue that we have a redox happening, right? Because elemental things are 0, right? And those are the only things that are 0. So, that's usually a big clue that what we're looking at is a redox process. All right. Very good. Here, activity series of the metals. We didn't talk about this last year. It was in your guys' textbook. I think we just omitted it. But here, what this says is, right, that these are most readily oxidized. These are less likely to be oxidized, okay? And hydrogen's in here as a standard because we can take hydrogen, elemental hydrogen, and oxidize it to H+, right? It behaves like a metal. And so if we look here, this is the easiest oxidation. This is the hardest oxidation, which should make sense because if we take a metal and we oxidize it, what does it always turn into? Ions, right? Solid metals become oxidized to their ions, which means that they are then soluble, right? Meaning that they form ionic compounds that can then dissolve, right, and turn into ions, which then makes sense that none of these are readily oxidized, because these are the things that, one, make up the piping in our houses, make up our jewelry between silver and platinum, which means that we don't want them to be readily oxidized, right? Going back to our lab with our silver alloy, that's why we had to use very highly concentrated nitric acid in order to get them to become oxidized, right? Which is what we did, right? We took solids and we oxidized them, right? And the nitrate was then reduced, right? And the hydrogen also over the course of our reaction, okay? And we'll see up here that the things that are most readily oxidized should make total sense, because where do we find lithium and potassium? Ding, 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 group 1, right? The most readily oxidized part, the most reactive elements in our periodic table come from that area, right? From group 1. And so it makes sense that those are readily oxidized, right? We never find this in nature. We find this all the time, right? This is not a natural state. We never find that because they are so readily oxidized. Yeah? Makes sense? Okay. Thank you for listening to this little extended note on redox and its processes. And be good. Stay tuned for the next one. See you guys later. Bye.